Drop a heavy stone into mud, and the resulting crater is the direct physical result of mass, gravity, and displacement. The state of the mud identifies the causal history of the stone. Digital information operates under a different logic. When a 0 switches to a 1 in memory, it occurs in a vacuum. It is a weightless symbol, severed from the history of how or why it changed. Physics is its own record. Information is not. Right now, the technology sector is struggling to guarantee the safety of artificial intelligence. When an AI model drifts from its alignment constraints, or when a prompt injection forces it to ignore security protocols, the industry treats these failures as software engineering bugs. These represent a class error, the inevitable failure of expecting digital symbols to behave with the unforgettable certainty of physical matter. To understand why, we have to separate all systems into two distinct computational classes.
Autocoincident systems are those where the physical state and the historical record of an event are the same thing. In detached record systems, the current state is structurally separated from the history of its creation. You can read the value of a bit, but the bit itself contains no signature of the actor that changed it. By design, all modern artificial intelligence software exists entirely within this detached record class. The current strategy for securing AI involves writing monitor programs to watch the main programs. But using one detached record system to verify another is a logical fallacy. You are relying on one symbol to prove the authenticity of another. This boundary between physical certainty and digital ambiguity is defined by the Autocoincidence theorem. To achieve true verification of an AI system, we must move past the attempt to verify software with more software. We have to cross the boundary back into thermodynamics. Ask a physicist a foundational computing question. When an information system overwrites a bit, where does the prior state go? In 1961, Rolf Landauer provided part of the answer, defining the concept of logical irreversibility. Landauer's principle proves that the physical energy of the erased bit is conserved. The universe balances the ledger by ensuring the energy from the overwrite dissipates outward as heat into the surrounding environment. But while the universe conserves the thermal energy, it erases the meaning of that bit. The semantic value, what that 0 or 1 actually represented to us, vanishes without an equivalent accounting. This creates what we can call the land of lost bits. Information systems are continuously leaking semantic history into nothingness. Semantic loss is not a physical event. Meaning is a human abstraction, and therefore it lacks physical conservation laws. Because that meaning is discarded the moment a bit is overwritten, detached record systems continuously destroy their own causal history by structural definition. The technology industry widely operates on the misconception that creating highly ordered, low-entropy digital systems will solve AI drift. This traces back to the origins of stochastic information theory and the work of Claude Shannon, who gave us the math to measure uncertainty. But entropy is a continuous measurement of disorder within a system. Computational class is a categorical distinction of what kind of system it is. This maps the relationship. The vertical axis measures entropy. The horizontal axis measures system class, splitting detached record from autocoincident. We test this by plotting a simple digital counter. Ticking upward by one integer each cycle, it sits in the low-entropy detached record quadrant. If we apply an edit test to this counter, we find a flaw. It is perfectly predictable, yet a malicious actor can overwrite its current value without leaving a physical trace. Next, a cryptographic random number stream sits in the high-entropy detached record quadrant. Despite high entropy, an attacker can silently swap the data stream with no physical evidence. Shifting to the autocoincident column, a single atom cooled near absolute zero sits in the bottom right. Finally, a turbulent box of gas sits in the high-entropy autocoincident quadrant. Notice the distinction. Regardless of whether the physical system is ordered, like the cold atom, or chaotic, like the hot gas, both contain their exact causal history within their microstates. Optimizing entropy within a software layer is futile for security. No matter how low you force the entropy, the system remains a detached record, vulnerable to traceless edits. If we cannot rely on entropy, is it possible to build a software auditor that recovers a detached record system's history from within its own code? The answer lies in the theoretical boundaries of computation mapped out by Alan Turing and his successors. When you build a complex verifier program to analyze a target AI model, both programs get trapped inside a mathematical boundary. This boundary is defined by Rice's theorem, formulated in 1953. It proves that any non-trivial semantic property of a Turing-complete program is mathematically undecidable from within that same system. Any trusted software-based verification tool is structurally incapable of providing absolute proof. It is ultimately just a story trying to verify another story. To escape this trap, we have to build a bridge that connects the detached record software class back to the autocoincident physical class. We have to descend entirely out of the software layer, stripping away the Turing-complete abstraction until we hit the unforgettable reality of the physical substrate. This is the function of an architecture known as ShortRank, which introduces a concept called geometric actuation. This shows the physical environment where the anchor point is located. Geometric actuation bypasses software entirely by mapping the AI's semantic role to a physical coordinate within the silicon geometry. Verification here relies on an XOR logic gate performing a direct electrical comparison. This specific gate escapes Rice's theorem because it operates strictly below the Turing threshold. With no program counter, with no recursion, and no loops, it cannot run software. It is purely combinational logic, making it immune to the trap of self-reference. Dropping below Turing completeness to a raw physical hardware address is the only mathematically sound way to anchor an AI's semantic claims to reality. When a live AI deployment attempts to execute an action, the request moves rapidly downward from the high-level software, triggering a hard physical reach into the memory architecture. This is the exact moment of verification. The authorization command is validated not by reading code, but by successfully reaching the designated electrical coordinate. At this fused operating point, the semantic identity of the AI, its physical position on the die, and the electrical hardware state become mathematically identical. We define an AI role as the strict geometric intersection of an acting entity and a targeted resource on the hardware. Because the meaning of the operation is now identical to the physical state of the gate, physical conservation laws suddenly apply. The semantic claim is protected by the energy and mass of the system. At this precise point, the architecture successfully achieves a point-in-time autocoincident verification. The event and the record are one. Relying on physical geometry to secure information is an ancient practice. Long before modern computers existed, early mathematicians like Pacioli built ledgers and records that were structurally autocoincident. Autocoincidence is the default state of the physical universe. History-erasing software is the anomaly. The hardware anchor does not invent a new concept in physics. It simply restores a physical constraint that early computer scientists sacrificed to achieve digital scalability. This is why philosophical alignment frameworks and legislative moratoriums will continually fail to secure AI. They attempt to govern the behavior of digital symbols while ignoring the structural limits of the medium. By shifting the verification problem away from software engineering and anchoring it to the hard limits of thermodynamics and computational complexity, this architecture removes the ambiguity of code. It forces attackers to do the impossible, argue against physics.